We have reached the final video in this course, and I saved one of the most important concepts for last. Every time your app works offline, every time it shows cached data, every time it lets the user edit something without checking the server first, your app is making a choice between consistency and availability. This trade-off is so fundamental to distributed systems that it has its own theorem, the CAP theorem. And even though CAP was designed for server-side databases, it applies directly to mobile development, because your phone and your server are a distributed system. Let me show you why this matters and how to navigate it in practice. The CAP theorem says that in a distributed system you can have at most 2 of 3 properties: consistency, availability, and partition tolerance. Let me define each one simply. Consistency means every read returns the most recent write. If user A updates their name to Alice on the server, user B immediately sees Alice, never the old value. Availability means every request gets a response. The system is always usable, even if some parts are having problems. Partition tolerance means the system works even when network communication between nodes is lost. Here is the key insight for mobile: network partitions are not optional. Your phone will lose connectivity. It is not if, but when. So partition tolerance is mandatory. That leaves you with a choice: consistency or availability. You cannot have both when the network is down. Let me make this concrete. Your app has a local room database and a remote server. The user is on the subway, no network. If you choose consistency, the app refuses to show any data that might be stale. The user sees loading screens and error messages until they get signal. The data they eventually see is guaranteed to be up to date, but the app is unusable without network. If you choose availability, the app shows cached data from room. The user can browse, maybe even make edits. The app feels responsive and usable, but the data might be stale. Someone else might have updated it on the server. The user might be looking at yesterday's version. Most mobile apps choose availability. Why? Because users prefer an app that works with possibly stale data over an app that does not work at all. But this choice has consequences that you need to handle. When you show cache data, you are accepting staleness. The data in your room database was accurate at some point in the past, but it might not reflect the current state of the server. For many use cases, this is fine. Showing a cached newsfeed that is 5 minutes old, no problem. Showing a cached bank balance that is 5 minutes old, potentially very problematic. The staleness tolerance depends on the domain. A social media timeline can be minutes or even hours, stale without anyone noticing. An inventory count should be as fresh as possible. Showing in stock when the item is actually sold out is a real problem. A financial balance should never be stale if the user is about to make a transaction based on it. For each piece of data in your app, you need to decide how stale is acceptable. This determines your caching strategy and how aggressively you refresh. One powerful pattern that embraces eventual consistency is optimistic updates. When the user performs an action, say liking a post, you immediately update the local state. The heart icon turns red. The like count increments. The UI feels instant. Meanwhile, you send a request to the server in the background. If the server confirms success, great, local state and server state are consistent. If the server rejects it, maybe the post was deleted or the user is not authorized, you roll back the local state. The heart turns gray again. The count decrements, you show an error. The trade-off is that the user briefly sees a state that might not be real. But in the vast majority of cases, the server confirms the action and the user experienced zero latency. The occasional rollback is a small price to pay for an interface that feels instantaneous. Twitter, Instagram, and virtually every social media app uses this pattern. When multiple users can edit the same data, conflicts are inevitable. User A edits a document offline. User B edits the same document offline. Both come online and sync. Whose version wins? The simplest conflict resolution strategy is last write wins. Each edit gets a timestamp. When a conflict is detected, the edit with the later timestamp wins. The earlier edit is discarded. This is easy to implement and easy to understand, but it has a significant downside. User A's work can be silently lost. They edited a document, thought their changes were saved, and then discovered they were overwritten by user B's later edit. For many applications, this is acceptable. User profile updates, settings changes, status updates, last write wins is fine because the latest version is usually the most relevant. For collaborative editing, documents, spreadsheets, shared lists, silently losing work is not acceptable. You need a smarter strategy. More sophisticated than last write wins is a merge strategy. Instead of picking one version, you merge the changes. If user A changed the title and user B changed the body, you can merge, take A's title and B's body. No data is lost. But merging has its own challenges. What if both users changed the title? Now you have a real conflict that cannot be automatically resolved. You have three options. First, prompt the user to resolve the conflict manually. Show both versions, let them choose or combine. This is what Google Docs does for simultaneous edits, though their real-time collaboration usually prevents conflicts from occurring. Second, use operational transformation. Instead of storing the final state, store the operations. Insert character at position 5, delete characters 10 through 15, and transform them to be compatible. This is complex but powerful. Third, use a data structure that is designed for conflict-free merging. These are called CRDTs. CRDT stands for Conflict-Free Replicated Data Type. It is a data structure that can be modified independently on multiple devices and merged automatically without conflicts. The math guarantees that no matter what order the operations are applied, the result converges to the same state. Think of a simple CRDT, a grow-only set. You can add items but never remove them. Two devices each add different items. When they merge, you take the union, no conflict possible. A counter CRDT works by having each device maintain its own counter. The total is the sum of all per device counters. Two devices each increment, no conflict, just add them up. More complex CRDTs exist for text editing, ordered lists, and maps. But CRDTs are complex to implement correctly, have larger storage requirements, and work only for data structures that can be designed around their constraints. For most Android apps, CRDTs are overkill. They are the right choice for collaborative tools like Figma or real-time shared documents, not for a typical CRUD application. The principle underlying all of these patterns is eventual consistency. In an eventually consistent system, if no new updates are made, all replicas will eventually converge to the same state. Your room database and the server will eventually agree, but not immediately. This is a weaker guarantee than strong consistency, where all replicas agree at all times, but it is a practical guarantee that works well for mobile. The convergence happens through synchronization. When connectivity returns, your app syncs local changes to the server and pulls server changes to the local database. After sync completes, the states match. Until then, they might differ. The key insight: eventual consistency is not a bug, it is a design choice. You are trading immediate consistency for availability and responsiveness, as long as you handle the convergence period gracefully, showing sync indicators, handling conflicts, merging data. The user experience can be excellent. Here is a practical pattern for handling conflicts that does not require CRDTs. Optimistic concurrency control works by assuming conflicts are rare and handling them when they do occur. Each record has a version number or an e-tag. When you fetch a record, he's ignored, you get its current version. When you update the record, you include the version you based your update on. The server checks, is this still the current version? If yes, apply the update and increment the version. If no, someone else updated it first. Reject the update with a 409 conflict. Your app then fetches the latest version, potentially merges the changes, and tries again. This is optimistic because you assume your update will succeed. No locking, no reservation. You only deal with the conflict in the unlikely event that it happens. For most Android apps, this is the right balance of complexity and correctness. Let me bring all of this together with a pragmatic recommendation for most Android apps. Use a local room database as your single source of truth for the UI. The UI always reads from room, never directly from the network. When data is needed, fetch from the server and write to room. Room emits the update via flow and the UI reacts. For offline support, show cached data from room. Indicate staleness if it matters. Last updated 5 minutes ago. When the user makes a change, apply it optimistically to room. Sync to the server in the background. If the sync fails, queue it for retry. For conflict resolution, use last write wins for simple data and optimistic concurrency for important data. Save CRDTs for collaborative features if you ever need them. This architecture is what the Android team recommends, what Now in Android implements, and what works reliably in production. It is not the most theoretically rigorous approach, but it handles the reality of mobile networking with grace. And with that, we have come to the end of this course. Let me share what I hope you have gained from these videos. Software is not magic. It is engineering, all the way down from Kotlin to electrical signals. Every abstraction you use, coroutines, databases, network calls, architecture patterns, has a concrete implementation with real trade-offs. Understanding those trade-offs does not make you a better code typist. It makes you a better decision maker. You now know why dispatchers.io is different from dispatchers default. You know why clean architecture helps some teams and drowns others. You know why your app needs timeouts, idempotency, and partial failure handling. You know why profiling before optimizing is not optional. And you know that consistency and availability are a trade-off, not a toggle. Take this understanding into your daily work. Question the patterns you use. Understand why they exist, not just how to implement them. And when someone tells you this is the right way to do it, ask right for what situation. The best engineers are not the ones who know the most patterns. They are the ones who know when each pattern applies. Thank you for joining me on this journey. Now go build something great.